Hello and welcome to the algebras. In today's lecture, lecture number 6, we will talk about solvable Lie algebras. So let's start with the definition of the derived series of a Lie algebra. Throughout the lecture, G denotes a Lie algebra over some field K. In the previous lecture, we defined the derived algebra of G, denoted as a bracket of G with itself, as the subspace of G spanned by all elements of the form a bracket of x and y, where x and y are arbitrary elements in G. We know that it is a subalgebra of G, moreover, it's an ideal of G. So now let's give the definition of the derived series of G. So we denote G upper 0, the algebra G itself, and for a positive integer k, we define the kth derived algebra G upper k of G recursively as the derived algebra of G upper k minus 1. An easy example, if G is abelian, then all algebras G upper k are 0 for all k greater than 0. A less trivial example, if the characteristic of our field is different from 2, then the Lie algebra GL2 over this field K has all derived algebras isomorphic to SL2. All higher derived algebras of GL2 are isomorphic to SL2. At the same time, if the characteristic of the ground field is equal to, then the first derived algebra of GL2 is isomorphic to SL2. The second derived algebra of GL2 is the linear span of the diagonal element H, and all higher derived algebras of GL2 are 0. Let us note that the kth derived algebra G upper k is a subspace of the kth component G lower k of the lower central series of the algebra G, and this holds for all k greater than or equal to 0. So now we are in the position to define solvable Lie algebras. A Lie algebra G is called solvable provided that there is a positive integer k such that the kth derived algebra of G is equal to 0. Alternatively, a Lie algebra G is solvable provided that there is a positive integer k such that the identity omega k is equal to 0 holds in G for an arbitrary choice of elements a1, a2, and so on, a2 to the power k. So here the identity omega k is defined recursively as follows. Omega 1 is just the commutator of two elements a1 and a2. Omega 2 is a commutator of two commutators of the form omega 1. So it's a commutator of the commutator of a1, a2 and the commutator of a3, a4. Omega 3 is a commutator of two commutators of the form omega 2, and so on. The identity omega k depends on the choice of 2 to the power k elements in G, and the algebra G is solvable if and only if there is a positive integer k such that omega k is equal to 0 for any choice of 2 to the power k elements in G. Consequence from this alternative description is that any subalgebra and any quotient of a solvable Lie algebra is solvable. Indeed, if G is solvable, then some identity omega k is equal to 0 holds in G. But then the same identity certainly holds in any subalgebra of G, so any subalgebra is solvable, and the same identity clearly holds in any quotient of G, so any quotient of G is also solvable. An easy observation, since the kth derived algebra is a subspace of the kth component of the lower central series of G, it follows that every nilpotent Lie algebra is solvable. Indeed, a Lie algebra is nilpotent if and only if some J lower k is 0, and in that case J upper k, being a subspace of G lower k, also must be 0. So every nilpotent Lie algebra is solvable. So let's now discuss the main example of solvable Lie algebras. In order to consider our main example, we make the following observation. Assume that we have a Lie algebra G and an ideal I in G. Then the algebra G is solvable if and only if both I and the quotient of G modulo I are solvable. Indeed, the only if part of this claim follows from the fact that any subalgebra and any quotient of a solvable algebra are solvable. So if G is solvable, then I being a subalgebra and G modulo I being a quotient, they must be solvable. Conversely, for the if part, assume that I and the quotient of G modulo I are solvable. So since the quotient of G modulo I is solvable, some derived algebra of it is 0. So this means that some derived algebra of G belongs to the ideal I. Since I itself is solvable, some derived algebra of I, let's say the m's derived algebra, is equal to 0. Consequently, the k plus m's derived algebra of G will be equal to 0, and so G is solvable. So now, as a main example, let us consider the Lie algebra B sub n of upper triangular n times n matrices, including the diagonal matrices. The claim is that this Lie algebra is solvable. And this is the case because if we take the commutator of this algebra with itself, if we commute two upper triangular matrices, then the outcome is a strictly upper triangular matrix, which means that the commutator of Bn with itself coincides with the Lie algebra n sub n of all strictly upper triangular matrices, which, as we know from the previous lecture, is nilpotent and hence is solvable. Moreover, n being the derived algebra of Bn is an ideal of Bn, and the quotient is clearly abelian because we factor out all commutators. And any abelian algebra is solvable. So this commutator, n sub n, is an ideal of Bn, which is itself solvable because it is nilpotent, and the quotient is solvable because it is abelian. So the algebra Bn is solvable by our observation above. So let's give yet another characterization of solvable Lie algebras. The claim is that a Lie algebra G of finite dimension M is solvable if and only if it has a filtration by subspaces such that each component of the filtration is a codimension 1 ideal in the previous component. The if part of the theorem is quite easy. If we have such a filtration, then we can do induction on the lengths of the filtration, and using the fact that each subquotient is abelian and hence solvable, we can use the observation from the previous slide to conclude by induction that all components of this filtration are solvable algebras. To prove the only if part, we need to find such a filtration for any solvable Lie algebra. We claim that the derived series of our algebra extends to such a filtration. In order to do that, for an arbitrary Lie algebra A, let us show that the inclusion of the derived algebra of A into A can be extended to a filtration by codimension 1 ideals. Let us choose some elements in our algebra A whose classes give a basis of the quotient of A by the derived algebra. Then we can extend the inclusion of the derived algebra into A in the following way. A is a linear span of the derived algebra and all these elements. So as a next component of the filtration, we take the linear span of the derived algebra with elements V2, V3, and so on Vr. Then we take the linear span of the derived algebra with elements V3 and so on Vr. And we take out one by one all elements of the basis, and at the end, the last component of our intermediate filtration will be our derived algebra. So in this filtration, here in between, we have r minus 1 steps. So altogether, the filtration has r steps. So since the quotient of A modulo the commutator is an abelian algebra, each component of this filtration is a codimension 1 ideal in the previous component. So it's a codimension 1 by construction, and it is an ideal simply because this quotient is abelian. So the commutator goes inside the derived algebra of A anyway. So since we can do it with any Lie algebra A in between it and its derived algebra, we can take a solvable Lie algebra G, consider its derived series, and use this trick to extend the derived series to a filtration as required by the formulation of the theorem. So this gives us an alternative characterization of solvable Lie algebras. The most important property of solvable Lie algebras is called Lease Theorem. So the setup for this theorem is as follows. G is a finite dimensional solvable Lie algebra, and we work over an algebraically closed field K of characteristic 0. The statement of the theorem is that every simple finite dimensional G module has dimension 1. Note that we work over an algebraically closed field K of characteristic 0. This is important. A corollary from this theorem is that every finite dimensional G module has a basis in which each element of G is represented by an upper triangular matrix. And here upper triangular means that this is a matrix which might have non-zero diagonal, not necessarily strictly upper triangular matrix. This corollary can be easily obtained from the theorem by induction on the dimension of the G module. So if G module has dimension 1, this is clear. If G module has higher dimension, then it has a simple submodule which has dimension 1 by the theorem. So we take it as a first basis vector, factor out, and proceed inductively. Another corollary from the theorem is the following interesting fact, that a finite dimensional Lie algebra G over an algebraically closed field of characteristic 0 is solvable if and only if its derived algebra is nilpotent. The if part of this corollary follows easily because the quotient of G by the derived algebra is abelian. So if the derived algebra is nilpotent, it is solvable. The quotient by it is abelian, so solvable, which means that G must be solvable. So the trick is to prove the only if part. And for the only if part, we can consider the adjoint representation of G. And by the previous corollary, the adjoint representation has a basis in which all operators of our Lie algebra, so all adjoint operators of X, where X is an element in our Lie algebra, are represented by upper triangular matrices. This means that the adjoint operator of each bracket of two elements in G is represented by a strictly upper triangular matrix. Therefore, if we take the commutator of G with itself and factor out the kernel of the adjoint representation, and the kernel of the adjoint representation is the center of G, so we have to factor out the intersection of the commutator with the center of G, we obtain that this quotient is nilpotent. At the same time, the intersection of the center of G with the derived algebra clearly belongs to the center of the derived algebra. So this shows that the quotient of the derived algebra by its center is nilpotent. And as we saw in the previous lecture, an algebra is nilpotent if and only if its quotient by the center is nilpotent. So we have proved that the quotient of the derived algebra of G by the center is nilpotent. This means that the derived algebra of G is nilpotent, completing the proof of our corollary. It remains to prove Lease theorem. The proof consists of several steps. The general approach to the proof, we prove the statement by induction on the dimension of the algebra G. The basis of the induction is a case when the dimension of G is equal to 1. Any Lie algebra of dimension 1 is abelian, so in this case G is abelian. And for an abelian Lie algebra, the claims that each simple finite dimensional module is one-dimensional is clear. However, a small remark, this is clear because we work over an algebraically closed field. So here, at this point, we use that case an algebraically closed field. If it is not, this statement is just not true. Okay, so now we need to prove the induction step. Because of our previous characterization of solvable Lie algebras, G has a codimension 1 ideal, which we denote by H. And we denote by G some element of the Lie algebra G which lies outside H. So Lie algebra G is generated by the element little g and the codimension 1 ideal H. So let V be a finite dimensional G module. Then, by restriction, V is also an H module. So by inductive assumption, V has a one-dimensional H submodule W, because all simple modules for H are one-dimensional by the inductive assumption, so V must have a one-dimensional H submodule W. So we denote by little w the basis of this submodule. Then, since capital W is one-dimensional, for any element h in H, when we apply h to our basis vector little w, we will get some scalar multiple of w. Let's denote by lambda of h this scalar. And this is true for any h in H. Because of the linearity of our action, lambda must be a linear functional on H. In other words, there is lambda in the dual space of H such that HW is equal to lambda of HW for any H in H. Now we can consider the set of all elements V in V with this property. So we consider the set of all elements V in V such that if we apply H to V, where H is an arbitrary element of our Lie algebra H, then H of V is equal to the scalar lambda of H applied to V. Because of the previous slide, this set contains our W, because the basis element of W has this property. So V lambda is a non-zero subset of V. We claim that V lambda is stable under the action of the Lie algebra G. Since the difference between the Lie algebra G and the Lie algebra H is this element little g, we only need to prove that the action of the little g sends V lambda to itself. How do we prove that? Let's take any element little v from V lambda. Set V sub 0 to be V, and for a positive integer I, define V sub I to be the i's power of g applied to V. So the linear span of all Vi's is definitely closed under the action of our little g. Since V is finite dimensional, only finitely many of the Vi's are linearly independent. So eventually some Vi is a linear combination of the previous guys. So let's consider how an arbitrary element h from H acts on these Vi's. On V, the action is by the scalar lambda of H because V belongs to V lambda. So HV1 is equal to HGV. So now we compute H in G. So we get GHV, and the price we have to pay in this case is the commutator of H and G. But V is in V lambda, and the commutator of H and G belongs to H because H is an ideal. So this gives us the first summand becomes lambda of H times GV, and the second summand becomes lambda of this commutator H and G times V. So if we apply H to V2, now we have HG square applied to V. Again, we can commute H all the way to V. We have to commute it past G twice, and then we get lambda of H applied to V2, because HV is lambda HV. The price we pay here when we commute is that we get the commutator of H in G. But this is again an element in H, which we again can commute farther to V. And when we push it all the way to V, we can use that the action of this commutator on V gives us a scalar lambda of Hg. So if we have this commutator only once, we take away 1 power of g, so we will have the scalar times v1 as many times as we have to commute it. For the vector v2, it's twice. So after the first commutation here, we will also have a summand the commutator of hg times gv. So on the next commutator, we will have such a double bracket, the commutator of h and g with g applied to v. This gives us again this kind of scalar. And we have 2 commutators here, so we take away 2 powers of g. Continuing similarly, it's clear that h times vi is equal to lambda of hvi plus a linear combination of vi minus 1, vi minus 2, and so on, with some coefficients, and also with the scalars given by lambda of some brackets between h and the element g. And these brackets can be multiple. So in particular, we can observe that when we apply h to vi, the coefficient at vi will be lambda of h. So the trace of the linear operator h on the vector space given as the linear span of all the vi's is equal to lambda of h, the diagonal element, times the dimension of this vector space. But we know that the trace of any commutator of linear operators must be 0. Since the dimension of the subspace is a positive integer and we work over a field of characteristic 0, this positive integer is invertible. So we can deduce that the value of our linear functional lambda on any commutator of h and g, where h is an element in h, must be 0. So here it's the same thing because the commutator of h and g belongs to h. So it's the same claim. It's very important that here we use that the characteristic of our field is 0. From the observation that the value of lambda at each commutator of h and g, where h is an h and g is our element, is 0, we have the following conclusion. So let's look at the second line of our computation. So if we apply h to gv, then we compute g and h, and the price to pay is the commutator of h and g, which applied to v gives us a scalar, but the scalar is 0. So this summons disappears. So the only thing left is lambda of h times gv. But this means that gv is an eigenvector for h with eigenvalue lambda of h. In other words, gv belongs to v lambda. So this proves that v lambda is stable under the action of g. Now we can easily complete the proof of Lease theorem. Since v lambda is stable with respect to the action of g, and we work over an algebraically closed field, g must have at least one non-zero eigenvector on v lambda, and the linear span of that eigenvector will be a one-dimensional submodule of v. If we assume that v is simple, it will follow that v must be one-dimensional. This completes the proof of Lease theorem. Thank you very much. Hope you enjoyed the lecture.